Good morning, scientists. Today we're going to look at geometric optics, specifically at mirrors. So some foundational information you need to know is that near the source of the waves are mostly circular. So we would see something like this, where the wave is coming out in this squiggly wavy line, crests and troughs. And if we picture them as ripples in a pond, we have all these ripples that are coming outward, and they come out in these different arrows. So notice that they would all be coming out, in every direction like this. But the farther away they get from the source, the more linear we would say those are. So if you imagine this really small arc here is continuing to move forward and forward and forward, then that's going to have very similar arrows that are all parallel to each other, so that the light from a distant source is going to come in parallel to whatever we're using that for. So first off, we need to talk about reflection, and that's when the wave bounces off of a surface. So we did this earlier in one of the labs. We have a flat surface such as a mirror. There's this orthogonal line or perpendicular line, and we have the light that's coming into this mirror, and it's going to be reflected out of mirror at the exact same angle. So these two angles are the same, the angle of incidence and the angle of reflection. Then nextly, we want to look at flat mirrors. What this does is it creates a virtual image that looks like it's somewhere in the mirror. So you're looking at this mirror here and you see the reflection of a candle, or maybe this is your curling iron or your shaving cream or something sitting in the bathroom that is sitting on the sink area. We would say that this is the real object. When you look at the lines that are coming up from that, well, we have to extend this line that you're seeing further back into the mirror, and it looks like that object is in the mirror. So if you've ever had the experience where you're looking in a mirror and it looks like it's a window that you're looking in, or maybe tonight, or this morning, when you're in the bathroom, look at the very edge of your vanity and very slowly move your eyes up the sink, up into the very edge of the mirror, and picture as if you're looking into a window. Like mentally tell yourself, I'm looking in a window, and that you're looking on the other side of the mirror or the other side of that glass window. So there's a whole nother bathroom on the other side of that. That's kind of the idea of what this flat mirror does, is it creates this virtual image that's on the other side of the mirror. Some key things you have to know then is that the image in the mirror looks like it's as far into the mirror as the object is actually from the mirror. So we have that the object distance, DO, and the image distance, DI. And notice that those two distances are going to be the same, that they're the same distance in as they are. Now, when we talk about spherical mirrors, so that was flat mirrors, we have two kinds of spherical mirrors that we're going to talk about. That's convex and concave. And in essence, what they're doing is they're taking, if you imagine a circle here, and you cut a chunk of that circle out, that's what a spherical mirror is going to be. It's that convex or concave. Now, the inverted side, so this side over here, is going to be our concave side, as if it's caved in, and the outside of it is going to be the bubbled side, is going to be the convex side of it. It's pushed out. Notice that the center of curvature, which is the very center of the circle, is right in the center of the circle, and that the focal point is going to be half of the center of curvature. So center of the mirror, which is C, is the imaginary center of the circle, or the center of the imaginary circle, and it's the radius of the circle. And then F is the focal point of the mirror, and it's half of the radius or half of C. And we'll look at that here in a second to see where that F comes from, or the focal point. So if I have a concave mirror, remember, because it's caved in on the one side, and I have these beams of light that are all parallel to each other coming in to hit it, what this concave spherical mirror will do is it will reflect all of that light back in through the focal point. Now picture again, if I draw and I'm not going to be able to draw this very well, but if I draw a perpendicular line to the circle at any one of these points, this angle of reflection and angle of incidence, or angle of the original ray and the angle of the reflected ray, they're both going to be the same angles, right? So that's one of the rules of reflection. They have to be the same angles. Same thing if I have one here. Terrible drawing there, but this angle and this angle are the same when they come off, and this is perpendicular to the mirror itself. So those are all going to focus through the focal point, which is why it's called the focal point, because all of those light beams are being focused into the focal point. Now, for the convex mirror, it works a little differently. Because it's bent the other way, it's going to push those rays away. Same thing though, these angle of incident, angle of reflection are the same. But if I picture all 4 of these rays that I have drawn here that are bent away, if I draw lines behind that extend them backward, they all go back through a focal point that's back behind the mirror. And that is the focal point of a convex mirror. So a concave mirror's focal point is on the same side as the caved in part, and a convex mirror is on the other side where you can't see the focal point for that. So some simple rules whenever we're drawing this. First off, you can draw as many rays as you want, but we need at least 2 and usually 3 rays in order to get where our images are going to be. So the first ray is going to be parallel to the axis and reflect through the focal point. Parallel to the axis and reflect through the focal point. The second ray is going to go through the focal point and reflect parallel to the axis. So notice that those are just flip-flops. So I can just shorten that by saying parallel, focal point, and then I'm going to have focal point parallel. And the very last one is going to be through the center of curvature, okay? Through the center of curvature, and then it reflects back to the viewer. So I have parallel, focal, focal, parallel, and then through the center of curvature. Now, what in the world does that mean? So let me show you. Oh, not yet. I'm not going to show you a picture yet. And then there are 3 things that we want to find out for each of those images. We want to know, is the image real or virtual? It's real if all of the reflected rays hit the image, and it's virtual if you have to draw any of those dotted lines behind the image. If any of the dotted lines, it makes it a virtual image, and if the reflected rays actually hit it, it's real. Upright or inverted, it's upright if it's going upright, and it's inverted if it's going the other way. And larger or smaller is just what it sounds like. Is the image larger than the original, or is it smaller than the original? So here we go. Here's an object. Here is what kind of a mirror is this? Yep, it's a concave mirror because the object is on the caved in side of it. And so imagine that mirror is part of a bigger circle. So we're dealing with a spherical mirror, not a parabolic mirror, and that the center of curvature is exactly in the center of that circle. And then where's the focal point? Remember, the focal point is halfway between the center of curvature and the mirror. And so if I draw my rays, the first ray is going to go parallel and then focal point. So I'm going to use a straight edge for this, a ruler that goes parallel to this bottom black line, and it reflects off of the mirror through the focal point. Then my second ray, remember, it flip-flops that. It goes through the focal point and then parallel. So I'm going to draw a line that comes down through the focal point and then bounces parallel to the thing. Now, we can already see that where these 2 lines meet, that's where my image is going to be from the axis. But we draw the third one just to be sure. So we have through the center and then back through the center. So notice that comes down through the center. It would reflect off the mirror and come back through the center. And then all 3 of those meet at that point, and that's where our image is going to be. Now, you'll notice that I have a little bit of a triangle here. If the mirror isn't set up right, or the focal or the center is not drawn correctly, that triangle could be bigger or smaller, but somewhere in the triangle is where that image is going to be. So now what we want to know is it real or virtual? So remember, real is when all of the actual rays touch the image. Virtual is when the dotted lines hit the image. So since these are all actual rays, it's going to be a real. And is it upright or inverted? So it's not upright, it's upside down, which is inverted. And is it larger or smaller than the original object? That is going to be smaller. So it's a real, inverted, and smaller object. Okay, next up is going to be a convex mirror. So at the center of a circle, circular center, center of curvature is going to be in the middle there, and the focal point is going to be halfway between the mirror and the center of curvature. And so what we're going to do is draw our first ray. It goes parallel to the axis. Now, because of the mirrors here, it can't come down through the focal point. It has to reflect off of the mirror away from the focal point. And if I draw a dotted line that extends back that way, you can already see where this is going. The second one is going to go to the focal point, but it hits the mirror and reflects, and it's going to reflect parallel. So I have focal parallel. Again, I'm going to draw a dotted line back behind there. And then lastly, I have one that goes through the center of curvature. So it goes down, hits the mirror, reflects back off, and then extend a dotted line, which means my image is going to be there. So here we go. Is it real or virtual? Do all of the reflected rays touch the image? And the answer is no, they don't. And so it's a virtual image. It looks like the image is in the mirror. Now, a couple of years ago, I asked a bunch of friends who are physicists, hey, is there anything you can see that's different about a virtual image versus a real image? And they said, not really. The virtual image just means that the actual light rays don't hit it. Your brain sees it where it really isn't. Is it upright or inverted? It is upright. And then larger or smaller, it is most definitely smaller. So this would be a virtual, upright, smaller image. Now, let's put some math to this. There are two equations that go with this. There's the magnification equation, which says that the height of the image divided by the height of the object is equal to the magnification. And or the negative image distance divided by the object distance is the magnification. And this is what I would call the hi-ho-dido equation. Hi-ho-dido. Hi-ho, which is your magnification. So notice that it's just ratios. In both cases, the i's are in the numerator, the o's are in the denominator. So think through that if I have a height that is twice as big on my image than the object, then I'm going to end up with a magnification of 2 because of that ratio there, which means that my object would be larger instead of smaller, right? The second equation, let's talk signs. Sign convention. For the heights, obviously, if it's upright, it's positive. If it's upside down, it's negative, because that just makes sense. And then it's positive if it's on the object side of the mirror. So whenever we had this, here's our concave mirror, and here's my object. If it's on this side of the mirror where the light actually gets reflected, then that's going to be the positive side. And on this side where you can't actually see it, that's going to be the negative side. You could say this is the real side of the mirror, this is the virtual side, which means a concave mirror is going to have a positive focal point, but think through, a convex mirror is going to have a negative focal point because the negative is on that virtual side. And then the last one is the mirror equation, and it should look kind of familiar to you, the form of it. If you remember when we talked resistors, that parallel resistors are that 1 over R equals 1 over R plus 1 over R. Well, it's the same thing for this. 1 over the focal point is 1 over the DI plus 1 over the DO. And all of the equations that you do, so there are two things that you would have to do in this. Either you would have to draw those images that we talked out there, or you're going to take these two equations and solve for different parts, either the magnification or solving for one of the distances or maybe solving for the focal point, and that's how you would do that. So in summary, we have our flat mirrors in the top right corner here that will create a virtual image that I have these dotted lines back, behind, and in the mirror. We have an object distance that is the distance from the object to the mirror itself, and the image distance, that's the distance from the mirror to the image. And then we have these other two kinds of mirrors that are spherical mirrors, are concave, so it looks like it's caved in towards the object, and are convex, that it looks like it's bubbled out towards the object. And the way that we would draw these is we would have 3 different rays, potentially only 2, but at least 2, usually 3. One is parallel through the focus, one is through the focus and then parallel, and then the last one is through the center of curvature on both of those. Now notice that in one image, it actually touches the reflected rays, and in the other image, we have to extend those reflected rays backwards into the mirror, and those dotted lines then are what determine whether it's real or virtual. So a real image is when the actual reflected rays touch the image, and a virtual image is when the dotted lines touch it. Upright is if the image is going upright or in the positive y direction. So this over here is upright. This one over here is inverted. And then smaller or larger. Is the image smaller or larger than the original one? And that, in a nutshell, is optical mirrors.